So I'm very pleased to talk about this two-dimensional or quasi-two-dimensional system as a modal system. That's the main message for tuning topological Dirac states. So the topic I will cover is linked to, broadly speaking, to the field of topological materials, and in particular to Dirac semi-metals. So there is a link with the nice presentation given yesterday by Leonardo De Giorgi about optical signatures of these semi-metals, and also to this morning's presentation by Massimo Capone about Hund metals, because we will see this system is a Hund semi-metal. And the basic point is how we can use electronic correlations to tune Dirac states, which are visible from ARPES measurements. I already show here in anticipated the results. So this work has been the result of a collaboration involving our laboratory in Paris, and then our colleagues in Orsay, École Polytechnique, and Soleil Synchrotron, and our colleagues in Trieste at CISA, Electra Synchrotron, CNR, and ICTP. And I should like to acknowledge especially give the credit to Nilou Nilfurushan, who just finished last year her PhD, among other topics about this system, and she has obtained and analyzed the majority of the ARPES data I will present under the supervision of Marino Marsi. The crystals were grown by our former PhD student David Santos-Cotin, who is now a postdoc in Fribourg, Switzerland. And I should mention a great contribution from various theoreticians, especially Michele Causula in our laboratory, Adriano Marici and Michele Fabrizio in Trieste, to model this system. And ongoing collaboration on this system are with other groups in Paris, in Fribourg, in Tsukuba, Toulouse, École Normale, and Columbia University with Professor Uemura. And I will mainly speak about results that have not been published yet. They are being the object of two papers here highlighted in bold, number 6 and number 7. The point is that we will show in these papers, in the first one, how we use electronic correlations driven by the cobalt nickel substitution. So how this substitution can tune the Dirac states. And in this second paper, how we can renormalize the Dirac states using light. So the first point I would like to address is to remind the importance of and the challenge of designing topological matter. And so mastering, this requires a mastering of the band inversion mechanism. And the second point is specific to the system we have been studying, is the possibility of using electronic correlations as a powerful control parameter of these Dirac states, which at this point I should say has been little studied, at least experimentally. And there are a few systems where this control parameter can be used. And the point is that barium nickel S2 is one of these systems, or at least that's what we pretend. And so that correlations can tune its topological semi-metallic properties. So we'll just recall the crystal structure, in particular the non-symorphic properties of this structure, which are crucial to understand the topological properties, the electronic phase diagram. So the first ingredient arising from the crystal structure and the electronic phase diagram is that the Dirac states are movable. That means they are located along symmetry lines and not at symmetry points, which is, to our knowledge, is quite unique and allows to exactly what we want, that we want to move and tune the Dirac states. And one possibility is just to move the Dirac nodes along the symmetry lines. And the second ingredient, which is necessary to forge topological states, is the spin orbit coupling. And I will show you that a quite large spin orbit coupling is obtained in spite of the fact that there are no heavy elements. And that's also peculiar of this system. And then I will go to the core of the results, with the ARPES evidence of tunable Dirac state using either the cobalt-nickel substitution or by using light. And finally, I will show that we developed a suitable theoretical framework based on an effective tight-binding Hamiltonian, enabling us to explaining these results and also to predict and how we can further change these states. And it will drive some conclusion perspectives. So as we know, Dirac and more generally Weyl semimetals are interesting as they display unique properties like chiral anomaly and chiral shift, which are responsible for remarkable properties like giant magnetic resistance and negative magnetic resistance, among other properties which I will not mention. I refer to recent reviews about this type of materials. And as control parameters of these properties, we have within a conventional band theory, so without taking into account electronic correlations, we have for sure band filling, spin orbit coupling, and the choice of crystal symmetry. And as already mentioned, non-symmorphic symmetry is crucial to add extra degeneracies at symmetry points. And and the last ingredient, which is peculiar of this of the system we have been studying, is electronic correlations, which has been studied in the past in very few systems like iridates or samarium hexaborides. However, these results are quite preliminary and still controversial. So I think the field of electronic correlation-driven topological matter is very open and very interesting. And as a matter of fact, the tuning of Dirac states have never been demonstrated experimentally in the solid state, only in optical lattices. So either there have been theoretical studies or experiments in optical lattices. And the message I would like to convey is that this tuning is possible experimentally in our system. And the reason is of this can be explained by various structural and electronic properties of this system. It's a quasi 2D system characterized by planes of either nickel or cobalt sulfur. The nickel or cobalt ions are coordinated in a pyramid, and the pyramids form a staggered or puckered structure. So you have alternated pyramid up or pyramid down in this structure. And in the cobalt side, we have a MOT state, actually a charge transfer insulator with antiferromagnetic order. And on the nickel side, actually with the substitution levels more than about 0.2, we have a semi-metal with paramagnetic properties. And the phenomenology is typical of that of MOT transition. Here I show the results by Shamoto-san, who will be the next speaker, who did a very nice job in the 90s to grow and characterize crystals So you see here the crossover from the insulating state to a metallic state as the cobalt is progressively substituted by nickel. So in summary, we have a quasi 2D, very simple tetragonal structure characterized by non-symmetric symmetry, crucial for the topological properties to be discussed. We have a Mott phenomenology with no structural distortions. That means only electronic degrees of freedom come to play here. We can forget about phonons. And as a function of doping, so X, we can tune the carrier density. In any case, the carrier density is quite modest, so typical of a semi-metal, about 10 to the 20 carriers per cubic centimeters. So we have, we can grow quite nice crystals, which can be easily cleaved. Here you have the AB plane or the tetragonal plane. So when we cleave crystals, we have a fresh plane of the cobalt or nickel sulfur that can be probed, especially by ARPES. That, as you know, is very important. And a simple ionic description tells us immediately why the system is so interesting, because going from the nickel side to the cobalt side, we have a reshuffling of bands. You see that the dz squared level, which lies above the dxz and dyz in the nickel system, is below these states in the cobalt case. And this reshuffling of bands is characteristic of, is driven by correlations, and favors the Mott state in the cobalt case, because as you see here, we have basically a half filling of 3 bands, which is favorable for obtaining a Mott state. So as Massimo Capone already discussed in detail this morning, the importance of the Hund coupling in these multi-orbital systems. We have studied these crossover theoretically and put into evidence the importance of the dynamical Coulomb repulsion in order to explain the crossover from a Fermi liquid to non-Fermi liquid picture across the phase diagram. And so you see that since on the nickel side we have Dirac semi-metal, we have here a playground to see how correlations can strongly alter the Dirac states. The evidence of Dirac states is immediate, straightforward from ARPES data. So this is one of the paper which is under review, where we show the existence of 4 Dirac nodes on the square plane of the Brillouin zone. And then there is another band here, which we will discuss later. So in the absence of this band, which could be eventually removed by changing the dimensionality of the system, we may have a pure Dirac semi-metal. And the interesting point is that this Dirac node lies, as I said, not at the symmetry point like in graphene or other Dirac semi-metals, but along the gamma M line. So in principle, we can move this node, and as I will show you, that this is indeed possible by using chemical substitutions. So we have movable Dirac points. The electronic structure can be accounted for by a non-standard approach. In fact, we spent quite a lot of time, and this is work mainly by Michele Casula in our lab, that we need an hybrid potential in order to take into account the non-local exchange correlation. And so this is the exact, the correct Fermi surface that we measure experimentally using ARPES or also quantum oscillations. So we have 4 Dirac nodes plus another modulated cylinder Fermi surface. The more standard approach using density functional theory plus LDA or GGA, or even DFT plus GGA plus U, doesn't account for this Fermi surface, and additional bands appear. What is constant in the independent of the type of codes used to describe and calculate the electronic structure, and the existence of Dirac cones pinned at the Fermi surface. And so this robustness of property, which doesn't depend on the code used, is explained by the Lattinger theorem. So that's interesting because that means that in the nickel system, so without doping, the nodes are pinned at the Fermi surface. So we have a true Dirac system. A second ingredient is the spin-orbit coupling. As you know, spin-orbit coupling is crucial in shaping topological properties. And remarkably, we have a large spin-orbit coupling evidenced by a Rashba effect. These are again ARPES data collected at the Cassiope beamline at Soleil synchrotron. And the Rashba splitting is very large, by the way, is basically a record value. And in spite of the fact that we have no heavy elements as electronically active elements. And the reason is that, by the way, we have 2 Rashba bands. The second one is just visible here. Is the non-symmetric symmetry, in particular the gliding plane associated with the Packard structure, which combined with the pyramid-like coordination of the relevant nickel and cobalt ion, which correspond of a crystal field and a large electric field, which has opposite direction in the upward and downward oriented pyramid. So that means that we have locally an inversion asymmetry, so that without spin-orbit coupling, in addition to the Kramers degeneracy, we have an orbital degeneracy. 1 and 2 labels the sides of the upward and downward pyramids in the unit cell. Whilst with the spin-orbit coupling, we have a partial lifting of this fourfold degeneracy. So the 2 Rashba levels are double degenerate, and they mix the spinor in the site number 1 with the spin down, with the same for site 2, and the spin up. Plus and minus indicates the spin orientation. And due to this local inversion asymmetry, we have a huge crystal field, which we estimated to be as high as 1.4 volt per volt times angstrom. So that's the large spin-orbit coupling, together with the DP hybridization, can generate this band inversion and the Dirac point along the gamma M symmetry direction. And we notice that we are close to a topological insulator. If the EU band was about 0.2 electron volt higher, we would have basically topological insulator, because the Dirac point is with the spin-orbit coupling generates a gap. And so the Dirac point is generated by the crossing of the A2U with the B2U bands. And so here we have calculated the hybridization gap of due to the BT hybridization for the three relevant bands P x squared minus y squared, xz, yz, and z squared. So in summary, we have the possibility of tuning the band inversion using as control parameters the dp hybridization, so that can be realized in experimentally using either pressure or strain. We can tune the spin orbit interaction using crystal field of nickel or cobalt, and we can use electronic correlation or doping, so that means cobalt substitution, or we can use the strategy or studying out of equilibrium states. So I will now spend the rest of my time to discuss about these 2 points using ARPES as an experimental probe. So I just take again the result already shown you about the nickel, so x equal 1 results. So you can have here a cross-section of the Dirac cones along the gamma m and the x prime direction. So you see these cones, in fact, are oval-shaped cones. So we have different speed of the Dirac quasi-particles along these 2 directions. And here we have energy cuts. So you have here a clear dispersion, the characteristic cone hourglass shape of the bands. And then you see immediately that as we dope with cobalt, we have a substantial alteration of these cones. Already the Dirac point is no longer lies on the Fermi surface, but is pushed upward. And we have a change in the shape. And the third element is that the bands are less well defined, and that is due to the incipient correlations. In fact, this doping is a doping which already displays a significant electron correlations. And as we dope further, so when we have 0.3 of nickel and 0.7 of cobalt, we have a fading of the bands that are no longer very well visible, and we still have the sign of the Dirac bands, but they are basically being suppressed. And so that's a clear demonstration how we can suppress the topological states using correlations. So I recall you here we are quite close to the critical doping corresponding to the metal insulator transition. Okay. So the last point I would like to, before talking about photoinduced renormalization of the bands, I would like to spend a few minutes about substantial theoretical work carried out by our colleagues in Casula, in Paris, and in Trieste, to develop an effective 2-band Hamiltonian where the relevant bands are the z squared and the x squared minus y squared or bands that form the Dirac bands. So alpha and beta is a label of these two bands. Kx and ky are the wave vector in the plane. And then we have that near the Dirac point along the gamma m line, we can linearly expand this Hamiltonian in order to have the characteristic well-known Dirac Hamiltonian, where the sigma x and sigma y are the Pauli matrices, and I is the identity matrix, and H naught, Hy, and the Hx are tight binding parameters linked to the tight binding parameters of this effective Hamiltonian. So thanks to this model, we can basically predict or explain how the Dirac bands evolve with X, with the substitution level. And this has been very successful because if we now compare the ARPES data, here we have a sketch of the experimental bands and the broken lines are just fit, is a fit of the experimental bands for the 3 doping levels. So you see, to summarize the previous results, we have that the Dirac nodes evolve towards higher energies, and we have that the Dirac nodes also move along in K-space towards the gamma point. Well, this trend is at least semi-quantitatively explained by the model. So these are now, is a model arising from this, expansion. So you see that both the position in energy and the momentum of the Dirac bands is well explained. So we are happy because of this good agreement, which can guide our experiments in the future.
Maybe we will ask Daniel now for his question, because maybe it's just to this point.
Well, maybe Daniel, if you don't mind, since I'm basically at the end, if you don't mind, I would prefer to conclude.
Okay.
Yeah, I mean, thank you. So the last point experimentally is the ARPES time-resolved experiment. So as you know, the time-resolved ARPES consists in a kind of palm probe experiment where you shine an intense light pulse at a certain energy, and with the delay delta t, which we can change, we probe the electronic structure with a different energy. So we are energy selective. And here you see quite remarkably a nice and change of the Dirac band. So we can, by using polarized light, selectively probe the dz squared component and the dx squared minus y squared component of the Dirac band. So in black, you have the equilibrium band, and in red, the out of equilibrium band after a delay of 250 femtoseconds. And here on the right, you have basically a zoom where we show the shift in energy and in wave vector of this branch for different times. So you see that already at 850 femtosecond, we are recovering the equilibrium band, and the same here for the dx squared minus y squared band. And again, the hybrid code I just mentioned before that correctly described the electronic structure accounts semi-quantitative for the trend. Here the arrow represents the evolution of the Dirac bands as a function of time. We have simulated the out of equilibrium states by changing the effective screening. So I think we can conclude by saying that I hope I convince you that the barium cobalt nickel S2 system is a model system of correlated topological quasi 2D material, and correlations allow to move from a Dirac semi-metal to a Mott insulator, that we are close to a topological insulator, that the system is characterized by strong spin orbit coupling as evidenced by a Rashba effect. That quite unique property of the system is the existence of movable Dirac nodes along a symmetry line, and that this allows for tuning the position in energy and momentum of these cones, either by cobalt nickel substitution or by using palm probe technique, so studying out of equilibrium states. So there are several open questions and perspective. I should mention just a couple of them. One is to probe these Dirac states using transport measurements. Leonardo De Giorgi has shown very nicely yesterday how this can be done using optical conductivity measurements. another probe, interesting probe, which is suitable to for this Dirac semi-metal is magnetotransport to probe the negative magnetotransfer and anomalous Hall effect. And another perspective is to control further the topological properties by going from a semi-metal to the insulator. As we said, the system is close to a topological insulator. And as already mentioned, we may use a pressure elastic strain, or we can play with the dimensionality of the system. We have indication from the theory that, for example, in the 2D limit in the monolayer, we would have, we may stabilize a topological insulator. So I thank you very much for your attention, and